is Millsap, and in this video, we are talking about orbital notations, which is something I know you've all been dying to learn, so it's your lucky day. To start off talking about orbital notations, I just want to talk about electrons and where they can be found in the nucleus. Well, you guys know that electrons are not found. Wait, did I say in the nucleus? I meant in the atom. Where are electrons in the atom? We know they're not in the nucleus, right? Because what is in the nucleus? Protons and neutrons, right? So outside the nucleus, whoops, I should go ahead and draw that, shouldn't I? Protons and neutrons are inside the nucleus. But what is outside the nucleus? Remember, most of the area of the atom is empty space, but floating in between that empty space around the nucleus are the electrons. The Heisenberg uncertainty principle may be something you've heard of before. It's a really famous scientific principle, and it states that you can know how fast an electron is moving, or you can know where it is, but you can never know both of them at the same time. And in our class, really all you need to know about the Heisenberg uncertainty principle is that what it means is that we can never know exactly where an electron is. We can be 99% sure we know where an electron is located, but technically that electron could be anywhere in the nucleus. So, what does this look like when we're talking about the actual atom? Well, right after Rutherford, there was a guy named Bohr. He was a little bit boring, scientist, and he came up with what's known as the Bohr model. And the Bohr model basically says that electrons are housed, or they can be found in different energy levels. And he's the one who first did the emission spectrum of hydrogen. And he said that the emission spectrum, like the little lines, the different colored lines, will tell us where electrons can be found. And that electrons essentially can only be found at one energy level at a time. So what do we know about energy levels? Well, I've listed 4 facts here on the left that basically tell us like everything we know about energy levels. The first is that we know that electrons have a negative charge. And we also know that things that are like each other, like 2 electrons that are both negative, they don't want to be near each other, right? They want to repel. That's really going to be important. Point. Energy levels can only hold so many electrons at a time, okay? And I'll walk you through exactly how many electrons each energy level can hold. But essentially, when an energy level gets filled up, it's not going to like keep adding electrons. Those electrons are then going to be kind of pushed to the next energy level because you can only house so many at a time because they don't like to be near each other. The other thing is that energy levels that are closer to the nucleus, they take up less space, so they can't hold as many electrons as energy levels are that are farther away from the nucleus. So the first energy level is the smallest energy level because it's closest to the nucleus. It can only hold 2 electrons because it's right there. It's really, really close. The second energy level can hold more because it's further away. It can hold 8. The third energy level holds 18, and the fourth energy level holds 32. Those are things that you will have to memorize and know that first holds 2, second holds 8, and so on and so forth. And as you notice, the number of electrons increases as the energy level increases, and that's because energy levels like 3 and 4 are much bigger than the first ones, which are much smaller, so they can hold fewer. So let's talk about how these electrons move in these energy levels. Well, in an energy level, the electrons spin in random patterns. We don't really know the patterns, but we can kind of know the shape in which an electron is going to move. For example, if one electron is spinning in this area or in this shape, and the other electron is going to be spinning in a different area or a different shape. And the question you should ask is why? Why do electrons spin in different areas or different shapes? Well, the goal is that electrons don't want to bump into each other. They want to avoid each other. So they're going to be spinning in different shapes or in different areas to avoid hitting each other. So think of an orbital as like a spinning area, okay? And orbitals are just areas of high probability. Remember, orbitals aren't permanent locations for electrons. It's just the most likely area that we would find an electron. So let's talk about orbitals. There's 4 different basic orbital shapes, okay? 4 shapes that electrons will move around in inside of an energy level. So I'm going to walk you through the 4 different types of shapes. The first shape is the s orbital. The s orbital is a circle shape, and so that means that electron can move anywhere inside that circle. There's only one s orbital or one s shape in every single energy level. There's only one s orbital. Each s orbital can hold 2 electrons, okay? So there's 1 electron here and 1 electron here. So the first 2 electrons in any energy level will be spinning in the s shape or the s orbital. The next one is the p orbital. There can be 3 p orbitals in every energy level. Each orbital, again, can only hold 2 electrons. So there's an electron, and there's an electron, there's an electron, there's an electron. So total, the p orbitals can hold 6 electrons, whereas the s, because you only have 1 s orbital, it can only hold 2 electrons. And the p orbitals will always come in like groups of 3. There'll always be 3 orbitals next to each other. So after the first 2 orbitals fill the s, then the next 6 orbitals are going to be filling up the p orbitals. Okay, so the d orbital comes in groups of 5. So there can be 5 d orbitals, and again, each individual orbital can hold 2 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So total, all of the d orbitals combined can hold 10 electrons. So the f orbital comes in groups of 7. So there's a total of 7 f orbitals in each one. Each orbital can hold 2 electrons again. So these black dots represent electrons. So total, the f orbitals can hold 14 electrons. Okay, so how do we actually use this in our periodic table? Well, let's say that I give you the element aluminum. On the periodic table, aluminum has 13 protons. So if we pretend that this element or this atom of aluminum is neutral, then those 13 protons would mean also that it has 13 electrons. So where do those electrons go? Okay, so I told you the very first energy level can hold 2 electrons only. So where are those 2 electrons going to go? They're going to go into the s orbital. So the way I write this out is I say 1s and I draw a box. The 1 stands for the energy level, and the s stands for the orbital. Okay, so the first 2 electrons, and I'm going to draw electrons with like arrows. So the first electron and the second electron will be in the 1s orbital. Now remember, the second energy level can hold 8 electrons, the third energy level can hold 18, and the fourth can hold 32. So if aluminum has 13 electrons, where are they going to go? Well, the first 2 electrons are going to go in the 1s orbital. The second orbital has an s orbital, and it has 3 p orbitals, okay? Because remember, the second energy level can hold 8 electrons. So 8 electrons will fit on the second energy level. So we have 2 in the s, and then we have 6 filling up the p orbitals. So how many total electrons have I filled up so far? Well, remember, 2 fill up the first energy level, 8 fill up the second energy level. So now I have 10 electrons, and I know where 10 electrons are. Okay, so 2 of them will be in the s shape or in the s orbital. And then now that leaves me at, and then the 13th electron is going to go in one of the p orbitals, and then the other 2 p orbitals are going to be left empty. Okay, so right now there's only 3 here. Okay, so one exception to this rule is the d's. If we have enough electrons, let's say we have something like 28 electrons, and the first 2 go here, the next 8 go here, the next 18 should go in the third level, but that's not really how it works. The 3d orbital is super weird. We actually fill up the 4s before we fill up the 3d, and so we fill up the 4s, then we fill up the 3d, and then we fill up the 4p after it. And if that's confusing to you, I'll talk to you a little bit more about how that works here in just a second. So let's talk about a couple rules. When you're doing orbital notation, there's some rules you have to follow. The first rule is the off-ball rule. That says that electrons will always start at the first energy level and you'll work your way up, okay? So, in this example, if we're going to do the example helium, helium has 2 protons, okay, because its atomic number is 2. So that means in its neutral state, it would have 2 electrons. So where are those 2 electrons going to go? They're going to go first in the first energy level. We're not going to put them in the second or the third because off-ball's principle says they would have to go to the first energy level, then we go to the second energy level. We're not going to do Pauli exclusion principle. You don't have to know that. But the second rule we have to know is Hund's rule. And Hund's rule says that electrons will not pair up in orbitals until they have to. Okay? And so I'll show you an example of Hund's rule in here in just a second. But if we did helium, the first electron we draw with an upward arrow, and the second electron we show with the downward arrow. And the reason why we do that is just to show that electrons are going to try and spin in different directions. So the first 2 electrons, which are the only 2 electrons in helium, are going to go on the first energy level. Let's do another example. Let's do magnesium. Okay, so magnesium on the periodic table has an atomic number of 12. And if it's neutral, that means its 12 protons will equal its 12 electrons. So let's assume that it's neutral and it has 12 electrons, okay? So where are these 12 electrons going to go? Well, the first 2 are going to fit on the first energy level in the 1s box, okay? The second energy level, remember, can hold 8, and the third energy level can hold 18, and so on and so forth. So if we have 12 electrons, we know the next 8 are going to fill up this way, and we always fill up the s orbital first because it's the lowest energy, then we fill up the p's. But here's how we fill up the p's. We're going to fill up the p's. Each orbital will fill up with 1 electron first before it will fill up the other p orbital. So the first p orbital has an electron, the second p orbital has an electron, and the third p orbital has an electron, but they haven't paired up, they haven't doubled up. So each electron's going to go to a p by itself first, and now we see that we have 1, 2, 3, 4, 5, 6, 7 electrons, and we need 12. So I have to put the 8th one here, the 9th one here, and the 10th one here, okay? So now they paired up because they have to. So I have 2 more electrons. Where are those 2 electrons going to go? They're going to fill up the 3s orbital. So I've started to fill up the third energy level, and I've filled up my s orbital. So here I have 3 s orbitals that are totally filled. I have 3 p orbitals that are totally filled. Okay, because here are my 3 p orbitals totally filled. And here are my 3 s orbitals that are totally filled. All right, now let's move on to another example. This is the example that I was talking about where we're going to have to fill up the 4s before we fill up the 3d. So think about the 4s goes first, the 3ds go second, and the 4p's go third. Okay. All right, so vanadium. Let's look at vanadium on the periodic table. Vanadium is in the middle. It's got a atomic number of 23. So where are these 23 electrons going to go? So right now, 2, 8, now I'm at 10. Okay, so I have to go to 23, 10. So this is 11, 12, 13, 14, 15, 16, 17, 18, and then I don't go, I'm going to forget how many I have. So I have 18 right now. I'm not going to go to the 3D yet. I'm going to first fill up the 4S. So this is 19, 20, and I accidentally switched my directions, which is weird. So then I go 21, and question, am I going to put one here or am I going to put one here? Okay, we want to put one in the next box because remember, you don't want to double up until you have to. This is 22 and then 23. What I want you to do next is I want you to do the orbital notation for carbon on your own, and we're going to go over it in class together. And that is it for today. You can now get started on watching 4.4 on electron configurations. Have a great day.